Okay, we're going to continue on working with applications that have to do with normal distribution and using the Z-score formula. Okay, this whole page is dealing with different height issues. Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a showerhead placement at 72 inches high. Okay, so again, we're going to be using this formula. We've got our mean, our standard deviation, and this is our x value. It's really important that you get them plugged in the right order. So we calculate this, we come up with a z-score of 1.21. We can go back to the normal z table. I need to go to the side of positive z-scores. I went a bit too far there. 1.21 would be this row and this column. So that comes out to be 0.8869. Okay, that is how we got this probability here. This statement here, again, is just meaning the probability that our z values less than 1.9 would be 0.8869. In other words, 88.69% of the population would fall below this z-score, or to the left of this z-score. Okay, but we are looking at, or needing to find, the percentage of men who are taller. This implies greater than this z-score. So we're going to have to use, this is implying that we need to use the complement rule. So we're going to have to take this away, this probability away from 1 to end up with 0.1131. This is the area to the right. So again, if you draw your curve, that's going to help you picture this a little bit better. Again, I like to put the values on the outside of my curve. I can kind of see that they're increasing in order. I like to put my z-scores in the lower part here, and then the shading in between, that's where our probabilities are. That's just one way to stay organized. So in this problem, about 11.3% of the population of men are taller than the showerhead. So design engineers might want to consider a higher placement to capture closer to 95%, because that tends to be what building codes are looking for. Okay, on our next problem, the bottom 5% of American adult men are considered unusually short. The top 5% of the American adult male men are considered unusually tall. What are the heights that separate these unusual heights from the rest of the population of the American adult men? I've got a note here that we're going to use the parameters from above, so in other words, the same mean and standard deviation. But the deal is I don't have an x value in here that I'm working with, but I do have the probabilities, so I'm working backwards somewhat. I'm going to be working with the critical values of 5% and 95%, so we need the z-scores that are associated with these probabilities, and that would be plus and minus 1.64. To kind of give you an idea where I found that 1.64, I go back to the probability chart, and I'm going to be looking for 0.95 or 0.05 in this, whatever's closest to it. So when I come down here, I'm looking at 0.9, I'm right in here, 0.9495, 0.9505, it's right in here. That is the row of 1.6, actually it'd be 1.645, but we're going to leave it at 1.64. And then when I go back to the other side of my chart, I'm looking for 0.05. As I roll around here, that's going to be down around here, 1.6, between right in here, these two columns, 1.645. That's what we're going to go with. Okay, so that is how I found these two. Continuing on with this problem, it's still a little bit weird, but we're going to be working backwards. We've got our z-score. We're going to have to plug that into the formula. You can see I've plugged that in, but I'm working backwards to find my data value, my x variable. So I think we've done this before, where we need to multiply both sides of the equation by this denominator. So that's what I'm executing here. My left side is going to be a negative 4.6. When I collect and try to isolate the x, I find that my lower value is going to be 64. In other words, a height of 64 inches would be that borderline value that separates the lower 5% from the upper 95%, and it equates or is associated with a z-score of negative 1.64. So now I need to do that same thing for the positive z-score of 1.64. When I'm carrying out that algebraic process, the left side of my equation is positive here, so I'll be adding to the 68.6 to come up with 73.2, which is the data value on the high end. That 73.2, you can't really see my decimal in there, is the borderline value that separates the upper 5% from the lower 95% and is associated with a z-score of 1.64. So these are the two data values that are associated with those borderline values that separate the lower 5% and the upper 5% from the rest of the population. Okay, our next one, we have heights of American women are normally distributed with a mean of 63.6 and a standard deviation of 2.5. We also know that heights of American adult men in this particular population are also normally distributed with a mean of 69 and a standard of 2.8. So we have parameters for two different populations here. We also have a data value for the female population. Lynn is 68.2 inches tall. What height does this relate to for men? So we have what we need for the female population. Let's go ahead and see what happens here. We're going to go ahead and plug that information into our z-score formula. We come up with a z-score of 1.84. I can go to the normal distribution chart, or I can do this on StatCrunch, and I'll find that the z-score of 1.84 is going to be associated with a data value of 68.2. It's also going to be associated with this probability of 0.961. So I've got my z-score, my data value, and the probability for the female population, for Lynn's placement in the female population. I need to know what that equates to in the male population. Now usually we're going to go ahead with the z-score. At this point, it doesn't look like I need the 0.9671, so I'm going to go with the 1.84, do that same process that we've been doing on this page here with our algebra, working backwards to find our data value. So when I work backwards, I find that I have a data value of 74.152. That is the height of males who equates or is equivalent to Lynn's height in females. So that's what we mean by relative to your population. Okay, so I want to show you how you can do these in StatCrunch. So I'm opening up StatCrunch. I need to make sure I have my paper here because I've lost my screen. So I'm going to go to Stats, Calculators, and Normal. We've been doing that for quite a few now. It's going to show us this default. We need to put our information in. So on our first one, we're going to have, totally lost my data here. We're going to have a height of, the mean height of men was 68.6. The standard deviation was 2.8. And we were looking at a shower head of 72. Remember, our data value goes in here. And then when we compute this, we can see that 88.8 basically percent of the population would be below this 72, but that isn't really what we need. Our problem is asking us to find the percentage of men who are taller. So that's kind of a tip that you need to choose the other sign, and we find that we have 11.2, and that's what we came up with in our problem. So you can see the picture really helps you if you've made a slight error there. On our next one, we've got the same parameters, 68.6 and 2.8. So I'm going to leave that in here, but I'm going to move this back just to kind of go back to the default. We need to know the data values that are going to equate with 0.05 and 0.95. So I'm going to put in 0.05. And I get this data value, which is exactly what we got. We rounded it to 64 inches. I want you to keep in mind here that our nowhere has a StatCrunch given us a z-score that equates to our data value. It immediately links us to the probability. So there's that step is kind of left out in this. I can show you how you can do that with StatCrunch, but it's a little convoluted and it's unusual that you would do that. So I need to do the other end of this where I am looking at 95%, and I'm going to leave this sign just so you can see what happens. This is going to show us 95%, the data value that separates the lower from the upper. Technically, we would want to look at it like that. The sign did, the numerical value didn't change whether we're looking at below or above our critical value. This is our critical value that separates the lower from the upper 5%. The lower 95% from the upper 95%. Okay, I'm going to close that because our next problem, we have different parameters that we're going to be entering, and I kind of want a fresh slate. So we're going to go to stats, calculators, down to normal again. This is where we had female and male population. I'm going to go ahead and put in the data that the parameters for our female population. We had a mean of 63.6. We had a standard deviation of 2.5. Okay, and Lynn had a height of 68.2, so far that's nothing real strange. So I calculate this, we can see that Lynn's height equates to a probability of 0.9671. You can see that I put that in our problem when we were looking here, simply because StatCrunch isn't going to give us the z-score. So really we need to think backwards, that we are going to need to put in the parameters for the male population and try to find the value that equates to the probability, the same probability of 0.9671 da da da. So I'm going to erase this. I'm going to put in the mean height for this problem for men was 69. The standard deviation in this problem for men was 2.8, and when I click compute, it retained this probability that we had calculated from the female population, and it provided us the data value that matches up in the male population. So that was how we could work through those three problems with StatCrunch.